In this lecture, we shall discuss an efficient method for proving that an abstract proposition is a contingency. Recall that an abstract proposition is a contingency if it's not a tautology nor a contradiction. So, thinking of the truth table for this abstract proposition, its column should not consist exclusively of ones, because then it would be a tautology, nor should it consist exclusively of zeros, because then it would be a contradiction. So in other words, a method to prove that an abstract proposition is a contingency would be to make a full truth table and considering the column for this abstract proposition, determining whether it does not exclusively consist of zeros nor of ones. Now this method is rather cumbersome, especially when we consider large abstract propositions with many proposition variables. Then a truth table for this abstract proposition becomes large. In this particular case, we have 5 proposition variables. So the truth table would consist of 2 to the power 5 is 32 rows. Each row of the truth table corresponds to a particular assignment of truth values to the proposition variables. And in fact, to determine whether a formula is a contingency, it is enough to find 2 of such assignments. One that makes the formula evaluate to false, proving that it's not a tautology, and one that makes the formula evaluate to true, proving that it's not a contradiction. In this lecture, we shall use this method to prove that this long formula is a tautology. And in this way, we can avoid making a full truth table. Let's start with proving that the abstract proposition is not a tautology. To this end, we should come up with an assignment that makes the abstract proposition evaluate to false. The abstract proposition is a conjunction, and hence, according to the truth table, it evaluates to false when at least one of the conjuncts evaluates to false. Let's focus on the leftmost conjunct. It is a negation, and a negation evaluates to false if the operand of the negation, in this case not A or B, evaluates true. Since a disjunction evaluates to true if at least one of the disjuncts evaluates to true, we conclude that under every assignment that assigns the truth value true to B, the disjunction evaluates to false. Let's confirm that indeed an assignment that assigns true to B makes the original abstract proposition evaluate to false. If B is true, then the disjunction not A or B is true. Hence, it follows that the negation not A or B is false. And since the original abstract proposition has not A or B as a conjunct, we may conclude that it evaluates to false too. Indeed, under every assignment that assigns the truth value true to B, we have that the abstract proposition under consideration evaluates to false, and hence it cannot be a tautology. In a similar fashion, we would now like to argue that the abstract proposition is not a contradiction. To this end, we need to show that it may evaluate to true. Since a conjunction evaluates to true only if both conjuncts evaluate to true, we need to find an assignment that makes each of the 3 conjuncts evaluate to true. As an important side remark, note that we should now find one assignment that works for all 3 conjuncts simultaneously. It is not enough to find a different assignment for each of the 3 conjuncts separately. Let's start with the leftmost conjunct. It is a negation, which evaluates to true only if its operand evaluates to false. Since the operand is a disjunction, every assignment that makes it evaluate to false should make both disjuncts evaluate to false. So we should assign false to B, and to make the left disjunct also evaluate to false, true to A. Recall that we should find an assignment that makes all 3 conjuncts evaluate to true. Let's now consider the second conjunct. It is an implication, which evaluates to true if either its left-hand side evaluates to false or its right-hand side evaluates to true. Since we already have assigned the truth value true to A, which is also the left-hand side of the implication, the first option does not apply here. We consider the second option. To make the conjunction evaluate to true, we should have an assignment that makes both conjuncts evaluate to true, and hence we should assign true to both C and D. It remains to consider the last conjunct. It is a by implication with false as left-hand side. So we need an assignment that makes the right-hand side evaluate to false too. Note that we now have a conjunction, and we also have committed to assigning true to C. So the only way to make the conjunction evaluate to false is by assigning false to E. Our assignment is now completely determined. Let's confirm that it indeed makes the original abstract proposition evaluate to true. If A is true, then not A is false. And hence, since also B is false, we have that not A or B is false. So, not A or B is true. Furthermore, since C and D are both true, we have that C and D evaluates to true. Hence, the implication A implies C and D evaluates to true. And since D is true and E is false, we have that C and E is false. So the by implication with false evaluates to true, and it remains to combine the three conjuncts. We conclude that the assignment that assigns true to A, C, and D, and false to B and E makes the abstract proposition evaluate to true, and hence it is not a contradiction. We have now found two assignments, one that makes the formula evaluate to false, and one that makes the formula evaluate to true. And hence we can now concisely present the argument that this formula is a contingency. If we assign the truth value true to the proposition variable B, then the formula will evaluate to false, proving that it is not a tautology. If we assign the truth value true to the proposition variables A, C, and D, and the truth value false to the proposition variables B and E, then the formula evaluates to true, proving that it's not a contradiction. And therefore, we may now conclude that the formula is a contingency. This concludes our presentation of an efficient proof that a long formula with many proposition variables is a contingency.